Hello everyone, my name is Sebastián Riquelme. I'm the Chief Operations Officer at the National Seismological Center in Chile. I'm going to show the new developments related to seismogeodesy, mainly W phase and finite fault models. This has been possible thanks to the collaborations we have now with the University of California, San Diego, the Pacific Tsunami Warning Center, and the University of Chile. So in the first slide, we have two figures. In the figures of the left, we can see all the type of earthquakes we have in Chile. We have thrust earthquakes, intermediate depth earthquakes, crustal earthquakes, normal faults in the ocean, and in the left figure you can see all the subduction large earthquakes that we have had in the past. We have the Valdivia 1960 earthquake, we have the Maule earthquake in 2010, the Illapel earthquake in 2015, the 1985 earthquake which was in front of Valparaiso, the Tocopilla earthquake in 2007, and the Iquique earthquake in 2014. Then you can see the profiles A, B, C, D, E, how the seismicity is pictured by the black dots, and how the Nazca plate is subducting below the South American plate. In the right figure you can see our network where we have our broadband sensors and how many we have been installing through the years. Okay. So here I'm showing the RTX GNSS network. This is an old figure, but we have a RTX model in our in all of our GPS sensors right now. At the beginning, the RTX were just installed in the instruments that were located in the coast. But right now, as I said before, all of them have the RTX model, okay? So what was the idea of having a broadband accelerometer and a GPS in the same place? At the beginning, we wanted to measure displacement, velocity, and acceleration at the same place. But of course, each one of these instruments have advantages and disadvantages. The broadband sensors clip in the near field. The strong motion the strong motion sensors don't clip, but you can't measure the whole spectrum to calculate magnitude. And if you want to integrate the strong motion, it's not going to work if you don't have a GPS collocated in the same place where you have the strong motion sensor. The broadband and the strong motion can pick the P wave, but the GNSS sensors cannot detect a P wave. So if you combine the strong motion plus the GPS, you can get a displacement and a velocity from Kalman filters, okay? And this can be very useful, for example, to calculate W phase or incorporate this new data into finite fault models. I'm going to show what we are doing at the center. So here I'm showing that this is a very old idea presented by Kiriaki in a paper of 1968, where he calculated for an earthquake in California. From the acceleration, he calculated velocity and displacement. So the same thing we can observe. In this case, these three quantities are measured by our strong motion sensors, our broadband sensors, and our GPS sensors. Here you can, in the strong motion and in the broadband sensor, you can see the P wave clearly. But in our GPS sensor, you cannot see the P wave, right? So the strong motion and the seismometer let you know the origin time of the earthquake, okay? So with that information, we use the GNSS component of our instrument, and we can measure the W phase for large earthquakes. In blue color, it's the raw signal, the displacement, and in red color, the W phase displacement. Okay, this is filtered between 200 seconds and 1000 seconds. Okay, so I'm not going to go into details of how you calculate the W phase, but you can get moment tensors from continuous GPS sensors. You have to be careful because the W phase shrinks in the near field, and you don't want finite fault effects when you're doing this. So you have to be you need stations that are far away from the source. We will say from 2 to 5 degrees of distance. And then on the figure of the right, in a paper from 2016, we calculate and we compare the moment tensors and the magnitudes that we obtained with our W phase method. We compare this with the USGS W phase magnitude and with the peak ground displacement magnitude that Diego Melgar proposed a few years ago. Okay, so the number of stations and channels that we have, of course, the Tohoku earthquake is by far the one that has more stations than any other earthquake. And this is what we are doing now at the National Seismological Center. So here, I just want to say that the response for the Chilean regional broadband network is typically, I would say, between 5 to 6 minutes. So we have a full moment tensor, and with the GPS instruments, we need a larger time window, but we can get a really good solution when these instruments are connected in real time. Okay, so that's one thing that we are doing now. We are calculating W phase with GNSS sensors and with broadband sensor. This is in real time. We haven't had a large earthquake to test the W phase with the GPS sensors, but we think with the seismogeodetic signals we can go to lower magnitudes. Okay, but we need a large earthquake, which we don't have right now, but hopefully we have a large, not so large earthquake soon. Okay, and the other thing that we are doing now, and this is also implemented at the United States Geological Survey at the NEIC, it's a real-time automatic finite fault model based on strong motion data and broadband sensors. This is work based on the paper of G of 2002. We have a bank of pre-calculation green functions from Su and Rivera, and we use the W phase centric moment tensor to define the fault plane and the seismic moment. The dimensions of the fault are estimated as 3 times the rupture velocity multiplied by the centroid time, okay? And we choose rupture velocity depending on the depth of the event. So if the event is too deep, we use larger velocities for the rupture, and if the event is too shallow, or we think or we calculate a tsunami earthquake, we use lower rupture velocity. And we remove the baseline of the strong motion using Wang's method, okay? What we have here is our operational time frame for the finite fault inversion with seismic and geodetic data. So at the beginning, I would say between 7 and 8 minutes, we can have the strong motion data and the GPS data, and we can have a very good idea of the extension of the fault and the slip patch that we can see in the first two figures. Then we just a few months ago we incorporated the W phase so we can measure we can constrain better the seismic moment, and then we incorporate teleseismic data with, of course, you have the surface waves and the P waves and the SH waves, but that takes longer time. And then we just incorporated INSAR data. Why INSAR data is important? INSAR data is very important for complex event, as for example as the Turkey event of this year in February, I think. So when you have complex events, the INSAR constrains very well the shape of the fault, okay? And you can see our results in this paper that I'm showing there, beyond detailization, okay? And why do we need different data? Because each signal, for example, the teleseismic signals are better to constrain the time and the space of the fault. The strong motion is very good for the time and for the space. The GNSS component is very good, and the W phase for the moment, and the INSAR, as I said, for the moment and for the space, especially for complex event. And tsunami and static GNSS are really good to constrain the seismic moment of the earthquake. So how to broaden frequency range? As I said before, we can use the strong motion, the accelerometer, plus the GPS. Using Kalman filters, we can get broadband displacement and broadband velocities, and we can see from zero frequency, from the permanent displacement, to very high frequencies in the near field. So this I think this is going to bring a lot of new observations in the near field in the future, okay? And just to finish, I'm going to show the example of the Tohoku-Oki earthquake with these signals. In the red dots, you can see the collocated GNSS and strong motion sensors. So of course they have a lot of instruments, but we have like 345 strong motions with GPS collocated, and the results are here. You can see the displacement obtained from Kalman filters in the upper figure, and the velocities in the near field in the figure below. So here you can see how you can see the P wave, you can see the seismic displacement. You see that this Kalman velocity, if you want to call it like that, is not clipped. So you can do anything you want because the signal is clean, it's not clipped, so you can measure anything you want. Okay, so now we incorporated these signals to our finite fault models, And the last example we did was this. We did the Tohoku earthquake again, but just with seismogeodetic velocity displacement from the Kalman filters. The seismogeodetic velocity is also obtained from Kalman filters, and with the W phase obtained from this signal. And the results are here. The moment rate function shows that the earthquake lasts between 180 seconds to 200 seconds with a peak moment of 1.2 joules. This exponent to 21. And here you can see the sleep map, which is very well correlated with all of the models that you can find in the literature, in the scientific literature. These blue stations are the one that we use for this inversion. And of course, this allows faster earthquake modeling, which leads us to faster tsunami modeling. We are going to have new studies of the near field. And of course, the most important thing is that the momenters and the finite fault models are going to be more accurate. So that's my presentation. I'm sorry I can't be there because of personal issues, but if you want to email me or anything you want, please write me. I'm happy to answer any question you have. Thanks for the invitation, and I hope you enjoyed my presentation.